Business science, sports science, food science, we love to put the word science behind other words. It makes those fields sound, well, more scientific. But if we are not careful, they will have more in common with pseudo-science. Data science is no different. Hi, I'm Connor and welcome to ADO. I recently moved from a data science position in industry to doing a PhD in machine learning. This forced me to reflect on the differences in which we approach problems and make decisions in industry and academia. I want to talk about those differences. Science is the best tool we have for understanding the natural world. So I also want to talk about how we can bring data science closer to the scientific process. Doing so will lead to a more reliable analysis and improve your ability to make decisions as a data scientist. Before we get into that, let's discuss what we mean by science. Science encompasses an enormous amount of human activities. Imprecisely, it is both the things we already know and the way we went about knowing them. The latter is called the scientific process. This is a systematic methodology for acquiring new knowledge. The most important part of that system is the hypothesis. A hypothesis is an educated assumption or guess about the way something works. A good hypothesis should be both testable and supported by evidence. You may not be sleeping well. A good hypothesis is the double espressos I'm having before bed are keeping me up. This hypothesis is testable. You could simply stop drinking coffee before bed and observe how you sleep. In other words, we are able to design an experiment that will provide data. An analysis of this data will provide evidence for or against the hypothesis. In science, we can never claim that a hypothesis is true with 100% certainty. We can only get closer and closer with evidence from multiple independent experiments. To claim that coffee has a negative impact on our sleep, we'd have to be a bit more rigorous than our once-off experiment. It would require multiple people, different levels of caffeine, double-blind tests, and so on. This is the scientific process. Make an observation, formulate an hypothesis, design an experiment, collect evidence, draw conclusions, and repeat. This is the best tool we have for acquiring new knowledge. Yet, it is not our only tool. On the surface, data science may seem close to science. Both are about seeking new knowledge. By nature, machine learning is also a repetitive process. We constantly try to collect new data and improve on previous results. But there are many cases where data science strays from the scientific process. The first is data storytelling. This is reframing an analysis in a way that doesn't bore a non-technical audience to death. We use pretty graphs and relatable stories to try to convince them that our conclusions are correct. A key part of data storytelling is building trust in a model. We need reasons for the features that we include and for the parameters of those features. In other words, we need to explain the underlying relationships captured by the model. The problem is, these reasons are thought up after the model has been built. We start with hundreds and sometimes thousands of features. After many iterations, we boil these down to the final set. It is only then do we come up with convincing business reasons for including them in the final model. This is the opposite of hypothesis testing. In some cases, we don't even care about how the models are making predictions. We only care how well they are making those predictions. The algorithms are treated as a black box, and we generate no new knowledge. This goes against the very goal of science. To make matters worse, this approach can jump from industry to academia. That is, machine learning researchers can create their own echo chambers. I'm sure you've seen examples of this, where paper after paper claim SOTA on some benchmark dataset. The goal of a study, or even an entire community, is to improve performance on these datasets. Diminishing improvements are taken as a scientific contribution, and the original research question becomes a second thought. The last difference has to do with the environments in which science and data science operate. Academics have the privilege of collecting new datasets or even testing an hypothesis in a completely new way. In industry, we do not have this privilege. You have to make decisions now with whatever evidence you have. This leads to the question, should data science be more like science? Often, the answer is no. It is simply not possible to collect multiple lines of evidence in the time required to make a decision. Yet, at the same time, science is still the best method we have for uncovering the truth. And there are some easy ways that we can bring data science closer to the scientific process. Firstly, it is important to discuss expectations with your colleagues before any analysis. This can be trends in your data or which model features you expect to be important. These can be taken as informal hypotheses. Your analysis will provide evidence for or against these expectations. If you find evidence to the contrary, it is now not enough to just provide a convincing reason. You will also need to explain why the existing expectations were not true. This puts a heavier burden on your reasons, making them more reliable. When providing evidence, don't just give one metric or visualization, as they all have their own limitations. Data scientists already do this. When assessing the performance of a model, you don't just look at accuracy. You look at other metrics like precision, recall, or even visualize performance using a ROC curve. This is similar to providing multiple lines of evidence for a hypothesis, but it's not the same as collecting new data or rerunning experiments. We are still using one data set, and all the metrics will be impacted by bias in this data set. We are simply removing the bias introduced by the metrics themselves. Taking this one step further, before we do an analysis, we can formally define what metrics we will use and what values are considered a success. This is to stop us from cherry-picking metrics that support pre-existing beliefs. Suppose you were doing the algorithm fairness analysis for a model. A lot of the time, this involves comparing model results for different groups of people using definitions of fairness. If you want to learn more, I actually have a whole playlist on algorithm fairness. Anyways, we must decide on definitions and cutoffs before building the models. If we don't, we may favor definitions that suggest the model is fair, or argue for higher cutoffs. Trust me, with months of modeling work on the line, this can become very tempting. We can also make an effort to not only use evaluation metrics. Interpretability methods like SHAP, LIME, PDPs, and ice plots allow you to peer into black box models and understand how they work. This brings us closer to the goal of science, as sometimes we can learn something completely new about our data. Up until now, we've really discussed problems that come from perversions of best practices. Often, data scientists are not the ones making the decisions. You are responsible for providing evidence based on data that supports a decision. You should strive to provide the most reliable information possible. When working in an organization, this is easier said than done. You will deal with multiple stakeholders who will all have their own preferences for a decision. Whether it's a manager who wants to get a model over the line or a business lead who wants to sell more insurance, pressure will be put on your conclusion. So, to avoid going from DS to BS, you need to stand strong and rely on what the data is telling you. This video is actually based on an article I wrote a while ago. It goes into a bit more depth, and there's a link in the description. Someone in the comments made a good point, and that's that data science can be used as a tool in science. I'd have to agree. or at least that they share the same tools. In academia, we have access to larger and larger data sets. As a result, we have to move away from traditional scientific methods and use tools that are common to data science. I've seen this in my own research, where I've been trying to process thousands of satellite images of the Irish coastline. But what do you think? Have I missed any important differences? Has your experience in industry been similar to mine? I'd like to know your thoughts in the comments. Also, I mentioned SHAP as a way for understanding your models, and it's really the most powerful Python package for doing so. If you're interested in learning more, I have a course that goes into detail on both the theory and code for applying this method. For a limited time, you can get free access. Go to the course page and sign up using this coupon code. You can also find a link to the course in the description. I hope to see you there.